Okay, time to go. I just got the cue. So we are on air, everybody. Welcome back to Discrete Math. And today we're going to finish up section 3.1. Check it out. I didn't even tell you. I didn't even mumble in my breath what I'm doing when I change the cameras. There we go. So, yes, today we're finishing up section 3. Oh, you can't see that at all. There we go. So section 3.1. I'm going to change this setup. There we go. And that is all about, right? This is all about predicates and things like that, right? This started out with saying, you know, statements are kind of limiting. Let's throw a variable in there, right? That's exactly what we're doing now. So first off, before you get to the exciting part, let's just kind of finish up, shore up some of the things we were doing last time, and work on being able to translate English statements into logic. So let's say we got a more exciting color. What are we doing? It's a Tuesday. Tuesday for purple. We should use Mardi Gras colors today. Okay, it might be exactly like 6 months to Mardi Gras. Maybe. That could be cool. Anyway, so that sounds right? So let's work on translating English to what I'm going to call logisterity, which is like all those made-up nerd languages, but more mathy. It just translates into logic. So, for example, if I had the statements, every natural number is a real number. How would you write that logically? There's me slowly dancing. Help. So every natural number is a real number. Well, every. Come on, what's that?
For all that?
For all, right? This screams of a for all statement, right? So what this is saying is that for all, right? And for all what? For all natural numbers. But remember with these for all statements and things like that, for all statements, this is a universal statement. Universal statements all go like this. They all say that for all x in some domain, we have a predicate being true, right? This is what a universal statement does. And what's really happening here is they take a statement like every natural number is a real number, and instead of looking at every natural number at once, instead it looks at a particular one. So this is saying for any particular x in the domain, p of x is true. But that's the same thing as saying for everything in the domain, p of x is true. But it's much better to look at one number because then one element, because then we can actually kind of talk about it. We can talk about this one element, where we can't really talk about every natural number at once, but we can't talk about any particular one, right? Hope that makes sense. If it works for any, that means it works for every. That should be obvious, but it's kind of a subtle point, but important point. So this is saying for all, let's say little n in the big N. And this symbol N with a bar, this means natural numbers. So this corresponds to this. For all of the natural numbers, N is in that, which is the real numbers right there. And by the way, is this true?
Yes.
Yeah. Because we have the chat's blowing up. Oh, that's been answering all my questions. Thank you. Yeah. Thanks, Benet. You got totally right. Yeah. So the other thing is that for all in the natural numbers is the real numbers, which is true. Now, we could not prove this with method of exhaustion quite because there's infinitely many natural numbers. That would be quite exhausting to go through and prove for all of them. You couldn't even do it. You ran out of time. We're all mortal. I don't want to make a question of mortality, but you kind of kick the bucket before you check every single natural number, and I would too. Actually, I wouldn't because I know a different method. But the point is, method of exhaustion is not going to work. But still, the same idea holds. The same idea is that this means every natural number is in fact a real number, and there is ways to verify that. Not really verify. There is ways to prove that, but we will talk about them in a later video. Anyway, so let's do another example. Another example would be some multiple of 4 is a multiple of 3. And I will call being a multiple of 4, right? The set of all multiples of 4, I'll call that, or I'll call x being a multiple of 4, this predicate m of x. Maybe I'll say m4 of x, as someone mentioned last time. I'll call being a multiple of 3, m3 of x. So basically, m4 of x is true if x is a multiple of 4, false everywhere else. M3 of x is true if x is a multiple of 3, false everywhere else. This isn't really standard notation, but I like it. Actually, the standard notation for this would be x in 4z. You can write it like that. But we're not there yet, so let's do this. So, how can I write this in logic, in the ancient language of the logic elves, logisterian? Oh, I gave it away. Crap. Okay. Anyway, yeah, so the sum here, the sum multiple of 4 is multiple of 3. That's saying sum doesn't mean that everyone works. This means sum. It means there's at least one, right? This is saying there exists, right? There exists, let's pick a letter. Let's say an M. In M of 4, such that, oh, so actually, no. This is actually good. I made a mistake. I made a mistake here, but this actually come up later. So remember this example. So if I'm saying some multiple of 4 is a multiple of 3, this is a multiple of 3. This M3 is still fine. That's saying something about, like I want to be able to plug in an X, and it'll tell me if it's a multiple of 3 or not. True if it's multiple of 3, false otherwise. But multiple of 4, I kind of want that to be my domain. So I don't really want that to be a predicate. I just want that to be a straight up set. So I'm going to call this set, I'm just going to call it D. So this is saying there exists an M in D such that M3 of M is true. So there's just an M in D such that M is in fact a multiple of 3. So another way we could have written this is that, like, if you made is a real number, if you made that predicate like R of N is a real number, then you can replace this with R of N if you wanted to. Right? It doesn't really matter. The important part is to recognize N is in R. That's a predicate, right? It's true depending on what N is. You got to plug it in. I feel like I'm talking a lot, but I hope this makes sense. We're kind of going over different ways you can write all this kind of stuff. Any questions? Okay, so next, let's say we have, oh, by the way, is this true or false?
Also true.
Also true. And we can use prove, I'll say, can prove with 12 as an example. Because 12 is a multiple of 3 and a multiple of 4. All right. Let's do at least one natural number is a real number. So is a universal statement or an existential statement?
Existential.
Existential, right? He's saying that the claim it's making about the natural numbers is just at least one of them. It's just saying about one of them, not all of them. So there exists an n in the natural numbers such that n's a real number. So you could say n is a real number, or if you want to name that predicate r of n, you could also say r of n. Doesn't matter. But yeah, is this true or false?
True.
True, right? Can prove with 1, for example. It'll totally work. The point is here, what I wanted to get at is that we kind of talk about how for all and their existence have this kind of yin-yang relationship. They're kind of opposites in the sense that the opposite of a universal statement is an existential statement. The opposite of an existential statement is a universal statement. And they're also, that kind of makes sense because they're kind of saying opposite things, kind of like the opposite of all of them is like one of them in a certain sense. But they're not, that's why I use the word yin-yang as opposite, because they're not quite opposite. It's kind of like how and or aren't quite opposite. So they have this yin-yang thing going on where just because for all in an n is an r, doesn't mean that there doesn't exist one. In fact, it does mean, right? If it works for all n, it's going to work for at least one n, right? These statements are the same thing except for the quantifier. And also notice that if it works for there exists, it doesn't mean it doesn't work for the for all. It might work for the for all, it might not. Does that make sense?
Yeah.
So unmuted and then muted, so I think that means yes. Okay, so let's move on. Let's say, what if we have sine of x equals 0 for all x multiples of pi. All right. Maybe I'll say whole numbered multiples of pi. And I will label this predicate p of x. So p of x equals, or equivalent to x is a whole numbered multiple of pi. All right. So what's the statement equivalent to? Is this a universal statement or an existential statement?
Universal.
Universal, exactly, because we have this for all. And what's our domain here, Safa?
It's. I think it's
I'll give you a hint. I kind of made
pi.
it again.
Like those whole numbered pies.
Those whole multiples of pi. Yeah, I don't really want to make this a predicate. I kind of want to make this a domain instead, although we're going to come back to this. So I'm going to make it a domain instead. So this is saying for all x in this domain right here, we're going to label something else. I'll label it for all x in this, I'll label it big pi. For all x in this domain, big pi, sine of x equals 0. So notice that sometimes in English, right, we kind of put the predicate first. This is kind of like those movies that get to like the most exciting part, where they go like, where like you see someone getting shot, and then it goes 3 days earlier. So like that's what this is. It's going sine of x equals 0. Isn't that interesting? Well, which x is? For all x's, they're holding multiples of pi, right? They kind of backfill what they're talking about in here. So that's why in logic we always put the universal quantifier. We always put the quantifier first, then the domain, then the predicate. Sometimes in English we kind of mix those things around, but it's important to know which ones are which, and I put them in order. So let's say we have, last one I'll do is A is odd. If A plus 1 is even for all multiples, sorry, no, for all integers a. All right. So is this universal or existential?
Universal.
Exactly. So we have a for all, and then we're using a, keep the variable a. So for all a, and what's our domain? What are we talking about here?
Integers A.
Integers a, right? We're making it clear about the integers, all the integers. So for all a and z, this is a symbol for the integers. It's a z. We'll talk about that again, but it'll be nice to have a little practice. So for all a in the integer z, and then what's my statement going to be? Or what's my predicate going to be?
A is odd if A plus 1 is even.
True. We could kind of write it like that.
Could you say A is an element of the set twice Z minus 1 or something like that?
Oh, I'm trying to do odd.
Yeah.
You're saying,
Oh wait, am I?
yeah, odd. The odd integers.
No, I'm not actually reading. I'm sorry.
The odd integers can't be written like this. That's actually totally fine notation. But we'll go all that later. But what I'm more getting at is that, so remember, a predicate becomes a statement if you plug in a variable. If you plug this in for the variable, right? So if you plug this in for a here, this is clearly a predicate. But if you plug this in for a, what kind of statement do you get? It's a very special statement.
If then?
If then, right? Like right now it's a predicate, but if you plug anything in, you get an if then statement. But normally are if then statements written in this order? What's the hypothesis here? What's the conclusion here? For example, is this saying that A is odd implies A plus 1 is even? Or is this saying A plus 1 is even implies A is odd?
The latter.
The latter. This is saying this guy right here. This is saying A is odd if A plus 1 is even. A is odd is conditional on A plus 1 being even. Right? So this kind of if statement kind of flipped on its head. Another weird thing we do in English all the time, right? But the way you can write it down here, but the way it would make sense as in logic would be saying A plus 1 is even implies A is odd. That's what it's saying. Because this says if A plus 1 is even, then A is odd. So the way you can write that is A is odd. I'm sorry. We just talked about this. You can say A plus 1 is even implies A is odd. And so notice it's kind of nice that like this whole thing is a predicate, but you kind of think of it as like a conditional predicate. It becomes a conditional statement if you plug anything in. But just like a conditional statement as a hypothesis and a conclusion. And here the hypothesis and conclusion both are also predicates. Well, so it's kind of weird. It's kind of like you did a conditional statement, but every word is a statement you replace with a predicate. I don't know. It's kind of fun. But anyway, yeah, you have this right here. And this is going to be true. And the way you prove it true is you have to prove it true for every single A plus 1 that's even. For every single integer in the thing. Cool. Any questions on that? Well, good, because you'll have a lot more of this to do on your homework. But honestly, it's like, I mean, this stuff is cool. This stuff is the basic stuff. This stuff is kind of like just the stage of understanding what a question's asking.